Hello everyone, welcome back to Medical Physics Academy. Today we're going to talk about coincidence timing and angular correlation in positron annihilation. In part of this experiment, the focus was on detecting gamma emissions from positron annihilation and calibrating the energy spectrum using sodium-22. With clear identification of the 511 and 1274 keV peaks, the groundwork was set. Now, in part 2, the goal shifts to exploring coincidence timing and angular correlation, two concepts that reveal how gamma photons behave after annihilation and how that behavior reflects fundamental physics laws like conservation of momentum and symmetry. When a positron annihilates with an electron, two gamma photons are produced, each with 511 keV of energy flying off in nearly opposite directions. But because the annihilation doesn't happen instantly after emission, timing becomes critical. Measuring the time difference between detections at two separate detectors allows us to confirm they originated from the same annihilation event. This is known as coincidence detection, and it's the basis of how PET scanners determine location. The smaller the timing uncertainty, the sharper the spatial resolution. I started with calibrating the multi-channel analyzer MCA to voltage. I began by generating pulses using a pulsar for each amplifier and monitoring them on the oscilloscope before processing with the MCA and recording the data on the computer. The pulsar was set to output voltages of 2, 4, 6, and 8 voltage, verified on the oscilloscope. The MCA was then calibrated accordingly as summarized in the table. After calibration, the pulsar was disconnected and the signal from sodium-22 received by detector 1 was displayed on the MCA. Amplifier gain was adjusted so that the 511 keV peak corresponded to 6 voltage. Next, the MCA was connected to the SCA single channel analyzer output with the SCA lower level set to 4.64 voltage and the window set to 0.121. This procedure was then repeated for detector 2. At this stage, the channel is converted to voltage in the MCA and only 511 keV energy peak is analyzed. Next, MCA calibration for time was performed using a gate and delay generator to introduce delays of 300, 560, and 700 nanoseconds. The corresponding MCA channels were recorded and summarized in Table 1. While the linear fit introduced some error, a quadratic model accurately predicted peak positions, confirming the MCA linearity is tailored for voltage, not time. A reference pulse was selected near the center of the screen and the MCA x-axis was recalibrated accordingly, setting the midpoint to 0. Deviations to the right and left were interpreted as positive and negative time offsets, respectively. To observe coincident pulses, we used the 560 nanosecond delay to synchronize pulses from both detectors. These ensured that true 511 keV gamma pair coincidences were captured while minimizing accidental coincidences. For angular correlation, the pulsar was removed and signals from sodium-22 were used. Detectors were placed at 180 degrees with the source at the center. PMTs were connected to the amplifiers and SCAs set to isolate 511 keV events. Chain 2 fed directly into the coincident unit, while chain 1 was delayed before entering the MCA. Data were recorded at multiple angles around 180 degrees. All measurements showed full width at half maximum if WHM values of approximately 3 nanoseconds, indicating excellent time resolution. The angular correlation plot showed peak coincidence in intensity near 182, slightly offset from the theoretical 180 degree. This discrepancy is attributed to residual momentum of the positron electron system and limitations in detector resolution. The count rate decreased at angles further from 180 degrees with increasing statistical uncertainty. In this experiment, two main types of errors were identified. The statistical errors due to limited data, such as insufficient counts at wider angles, and systematic errors such as electronic drift or detector misalignment. To improve accuracy, increase measurement time, or use a higher activity source to boost statistics, keep measurements near 180 degrees where count rates is high, calibrate SCAs daily to reduce drift, use faster electronics for better time resolution, employ laser-based detector alignment for improved geometry, optimize energy windows, apply shielding, and correct for random coincidences to reduce accidental events is advised. In this part, we advance from energy detection to precise timing analysis and angular correlation of 511 keV gamma photons. By calibrating our system for time delays and aligning coincident pulses, we demonstrated the ability to accurately capture true annihilation events. We also investigated angular distribution consistent with theoretical expectations. We discussed key sources of error and proposed several methods to enhance accuracy. This part of the experiment brings us closer to understanding how real-world PET imaging systems operate, reinforcing the connection between nuclear physics experiments and practical applications in medical diagnostics and therapy. Thanks for watching. If you found this experiment insightful, don't forget to like, subscribe, and share. Stay tuned for more physics demonstration and applications in medical imaging and beyond.